Okay. So on number 8, you guys were working on this. We were supposed to verify these identities by trying to get the left side to look like the right. So remind me what we said might be a good way to start. When you look at this, which side would you want to start with? The left. And the reason is? That's right. We start with the side that looks more difficult. So I have this plus this, and I notice that these fractions do not have the same denominator. So what did you decide you might try to do?
Common denominator.
And what would be the common denominator? Well, is 1 minus sine of x the same thing as 1 plus sine of x?
No.
And they don't have any common factors, do they? Because a factor would mean I would be able to write this as something times something, and 1 and sine of x don't have anything in common except 1. So this is sort of like if I had a fraction and this was a 2 and this was a 3. They don't have common factors and they don't match. So what ends up being your LCD? You have to do what? Multiply them both together. So my LCD is going to have to be 1 minus sine x times 1 plus sine of angle x. Okay? And that would mean that this first fraction has to get multiplied by what? Which part do I not have?
1 plus sine of x.
Good. So I'm going to multiply that times 1 plus sine of x over 1 plus sine of x. Then this second fraction doesn't have which part?
1 minus sine of x.
Good. So let's multiply that by 1 minus sine of x over 1 minus sine of x. How many of you figured out that was how you wanted to start? Okay.
Can you take a pause real quick?
Absolutely.
Yeah.
I'm just trying to catch up or understand.
Think you've got a great idea. We want to write it as one big fraction. So if I multiply these pieces together, wouldn't you agree? I have 1 plus sine of angle x in the numerator, but the denominator is both of these pieces, 1 minus sine x times 1 plus sine of angle x. Okay? Plus what will be in the numerator of the second fraction? 1 minus sine of x over the same denominator. Okay, since the denominators are the same, we can actually add these two, right? And what's going to end up being in the numerator when we add these? Well, be careful. I've got 1 plus sine of x plus 1 minus sine of x. What happens to the sine of x's? They cancel, but do the ones cancel? So 1 plus 1 is 2 over, now that denominator is 1 minus sine of angle x times 1 plus sine of angle x. And I'm thinking at this point, there might be an advantage if I actually multiply these two together. Because what will that give me if I multiply them together?
1 minus sine squared.
1 minus sine squared of angle x. That's a difference of squares because the outer and the inner are going to cancel out when I use FOIL. And I'm left with 1 minus sine squared of angle x. Now let's take a peek at where we're trying to go. We want to end up with 2 times secant squared of x. Any thoughts on how that might come about? I see the 2. I'm excited about that. How could I potentially get there? And I'm going to give you a hint. Think Pythagorean identities. Do you see a replacement for 1? Oh, I think Megan sees it. What?
Isn't that equal to cosine squared?
Very good. 1 minus sine squared x can be replaced with cosine squared x, correct? Right? I know it's been a weekend since we last met, but cosine squared of x plus sine squared of x equals 1. So when you rearrange that, 1 minus sine squared of x would equal cosine squared of x. Oh, we are so close because we're trying now to get from 2 divided by cosine squared of x to 2 times secant squared of x. Is it possible to get there? Because on this one, we said we used a Pythagorean identity. What do we need to use here? A reciprocal. We need a reciprocal identity because we could think of this as 2 times 1 over cosine squared of x, right? And the 1 over cosine squared of x is the same as what? What's the reciprocal of cosine?
1
Secant. This is the same thing as 2 times the secant squared of angle x, which is where we were trying to go. We just got the left side to equal the right. Okay, did that make sense?
No.
All right, you say no as in,
Okay,
where did you get stuck?
Right there on the 1 minus sine squared x.
Mm-hmm.
Break it down.
Okay, so we were good until we got here,
Yes.
and then after that, it's trying to figure out where to go.
Let's go back, I'm sorry, let's go back one more step to where you got the 2 from.
Okay, all right, let's kind of talk our way through it. And if we get to a point that you say, wait a minute, explain that more, we'll stop and talk about it in a little more detail. So we understand the idea that if there are 2 separate fractions, we got to get a common denominator, combine it to a single fraction. So that's why we multiplied by something that was equivalent to 1 in order to get common denominator, right? And then multiplying these together gave us 1 plus sine of x in the numerator here. Multiplying these together gave us 1 minus sine of x in the numerator here. We already know what the common denominator is. Now, since there's a plus sign, I'm just adding up these terms. I'm going to come over here so you can see it. 1 plus sine of angle x plus 1 minus sine of angle x. I'm just adding those 4 things together. And if I were to put together like terms, the positive sine of angle x and the negative sine of angle x canceled out. And the 1 plus 1 is how we got the 2. Okay, so now we're good here, right? And we understand if we use FOIL and multiply these together, that's where the 1 minus sine squared x came from, right?
So they wouldn't be squared, right?
Because they're not the same. See, one's got a minus sign, one's got a plus sign. So I use FOIL.
So since you're adding in their common denominators, you don't have to like bring it down twice. Like since it was on that side.
Okay, so you're saying because we're adding these, the reason we did this was to get the common denominator so we could add them. And so it's the same idea as if you had 1/4 and you add another 1/4 to it. What does that equal? 2 over 4, because you keep the same denominator and you just add the numerators.
Oh, okay.
So that's what we did. We kept the same denominator and we just added the numerators. And then to clean up this denominator, because it's this times this, we use FOIL. And when you multiply first times first, that's where you got the 1. Outer was a positive sine of x, inner was a negative sine of x. That's why those canceled out. And last times last is where the minus sine squared x came from. Okay? So at this point, we're now trying to figure out where we would go from here. And anytime you see one of these trig ratios squared and there's a 1 with it, that's when you want to check to see, could I replace it with a Pythagorean identity? And so if you double check, since cosine squared of x plus sine squared of x equals 1, if I rearrange that, I would get 1 minus sine squared of x is equal to cosine squared of x. Does that make sense? That Pythagorean identity, if you look at it on here, sine squared plus cosine squared equals 1. All we did is subtract sine squared from each side, and 1 minus sine squared would equal cosine squared. Okay? Does that make sense? And then, since we were trying to get to secant squared, that's when you want to think about reciprocal identities. Because remember, our C's and our S's pair up on those reciprocals. Since cosine's in the denominator, it can go up to the numerator and become secant. And that's how we got to the end. So that's using a lot of the identities here.
But 2 times 1 on the reciprocal, you like count with the
Basically, here's what I did, just to make it more obvious how we're using the reciprocal identity, is you could think of this as, with 2 being in the numerator, it would be the same thing as 2 times the fraction 1 over cosine squared of x, okay? And if I have 1 over cosine squared of x, then I can see, oh yeah, if I flip that, the reciprocal of cosine is secant squared, okay?
I'm guilty on this.
Awesome. Okay, so this 7-1, 7-2 is practicing applying these identities. Just in 7-2 in particular, you've got equations, you're trying to get the left side equal to right. 7-1 is mostly replacing to see if you can clean things up somehow. And usually the instructions will write it where you don't have a quotient, or it just told you to replace everything with sines and cosines and clean up as much as you can. So did we end up with any other questions from homework, or are you feeling somewhat okay? Let's start with 7-3 then. So here we go. We've got other types of identities that we need to practice, and we're going to start with sum and difference identities, okay? Now, in order to use these, there's one thing you have to recognize. First of all, I don't know why it prints out as a little p, but this should be pi, okay? So let's say that angle A is equivalent to pi over 2, and angle B is going to be equivalent to 0. And what I want to show you is, if I'm taking the cosine of angle A minus B, that's not the same thing as the cosine of A minus the cosine of B, okay? So if we use pi over 2 for angle A, and we use 0 for B, that's going to give us the ability to use, which would we need, hala or a hala if it's cosine? Hala, because it starts high. All right, good. So that will give us something easy to work with, and we can tell what goes on here. So if we just replace A with pi over 2, B with 0, then that would mean pi over 2 minus 0 is just pi over 2. And what is the cosine of pi over 2? Cosine, we said, was hala. And so if we're starting at an angle of 0, then when you get to pi over 2, it's at an axis. And so high is 1, the axis is 0. So we would get 0 there. You guys are right. Okay? Now, if, on the other hand, I look at this and I say cosine of A minus cosine of B. Notice this was written this way, okay? Cosine of, in parentheses, A minus B. And we said, okay, let's just subtract angle A minus angle B. We'll take the cosine of that and see what we get. This is saying, all right, distribute it through. Let's see what the cosine of angle A minus the cosine of angle B is. So the cosine of angle A is pi over 2. Actually, let me do it this way. And B would be the cosine of 0. Now, the cosine of pi over 2 is 0. We just found that a minute ago. Minus, what's the cosine of 0? Is 1, isn't it? Because remember, it starts high. So the cosine of 0 degrees has a ratio value of 1. Well, what is 0 minus 1? These are, oops, -1. These are not equivalent. They're not the same. So what I'm trying to show you is I cannot, when I see this, I cannot just think of it as distributing through and write it this way, because these are not giving me the same thing. When I actually put angle values in, if I subtract here and get an angle value and I take the cosine of it, that's a different number than if I took the cosine of this and subtract the cosine of that. You see what I'm saying? So we've got to figure out, what am I supposed to do when I am given this? Then this is going to be our difference identity for cosine. And if you were to look on your sheet, here's what you would see. There are sum and difference formulas here. Now, the way you read it off your sheet is this. They're going to have a plus sign over a minus sign. That means if you're using the plus sign, you're going to use whatever is on top whenever you look at this over here. If you're using the minus sign, you're going to use whatever SIGN is on bottom. So here's what these formulas are. The cosine of angle A plus B is going to have to end up being the cosine of angle A times the cosine of angle B minus the sine of angle A times the sine of angle B. Okay, now, there's a little pattern to that. With cosine, I keep my cosines paired up. When I multiply, and I keep my sines paired up. And then what do you notice about your SIGN? Does it stay the same or does it change? Changes. So if I'm taking the cosine of a sum of angles, I'll multiply the cosine of each angle together and subtract the product of the sines of each angle. Now, if it's the cosine of a difference, guess what changes? The only thing that changes is going to be your SIGN. So if it starts with a minus sign here, I'm going to put a plus sign here. But I'm still pairing up cosine times cosine and sine times sine. All right? And these are on your sheet right here. Remember, you're just going to follow the pattern. If I want the plus sign, I've got to use the SIGN on top. If I want the minus sign, I'll use the SIGN on bottom. Okay? But there it is right there. Now, here's why this might be helpful. We want to find the exact value of the cosine of -75 degrees. Now, ask yourself a question. Is that a special right triangle angle? No, we do not. We have a 30, we have a 45, and we have a 60, and we have all those quadrantal angles. I have no idea what the cosine of 75 or -75 degrees would be. So, can we figure out some way to write this?
Yes.
Okay, very good. Now, there's a, you're confident, you know it's possible. I like it. All right. So, here's one thing we might want to consider doing. Does it bother you a little bit? There's a negative sign there. No? Okay.
Just means it's spinning the other way.
That's true. And we could actually put these in the quadrant and we could work with it that way. Here's the other thing we could do. Remember how we talked about the even and odd formulas? If I have the cosine of a negative angle measure, it's going to be equal to the cosine of that positive angle measure. In other words, I don't even have to worry about putting them in the fourth quadrant if I don't want to. It will still give me the same value. But don't automatically assume that, because if we were working with the sign, we would have to put a negative sign in front, okay? But we'll keep it negative. I just want to show you, you could recognize that's the same thing as the cosine of +75 degrees by using that even odd property. But we can keep it negative if you want. Now, here's the trick. I want to rewrite this so I'm either adding together or subtracting two angle measures that are special right angles that I would be able to calculate. So what would be a pair of numbers I could either add or subtract to get -75?
No. 45.
So we could maybe use 45. What would we need to use with it to get 75?
Oh, 7,000.
30. Could we do like a negative 45 plus a negative 30?
Yes.
Sure could. Okay. So why don't we write it that way? We could do a negative 45 degrees plus a negative 30 degrees. Because those are equivalent, right? Okay. But the problem is, I know I can't just do it this way or this way. I'm going to have to use one of these formulas. All right. So tell me how we would write this. We'd have the cosine, because we start with cosines first, of what would we do first? Yeah, this is like your A, this is like your B. So cosine of
Negative 45.
negative 45 degrees. Then what? Times cosine of negative 30. Good. Now what SIGN do I need? Well, I have a plus sign here, so I'd want to put a minus sign. Good. And then I'll put sine of negative 45 times sine of negative 30. Okay. Now, the one thing you'll have to be a little bit careful about here is by keeping the negative signs, we will have to be careful when we put the SIGN on these ratios, because that means we're now working in the fourth quadrant. So you might want a 45, 45, 90 and a 30, 60, 90 that you draw in the fourth quadrant, and let's label those sides. So when it's a 45, 45, 90, here's my right angle. That means this is 1. What's this side length? Negative 1. This one is good. Okay, if this is my 30, what's this side length? Negative 1. What would this side length be? Square root of 3. And my hypotenuse is 2. Okay, so those are going to be my triangles that I'm going to use to help me replace these values. So the cosine of negative 45 is going to be what?
1 over the square root.
Yeah, cosine is adjacent over hypotenuse, so that's going to be 1 over square root of 2 times, what's the cosine of negative 30? So if I go down here to negative 30, cosine is square root of 3 over 2. Minus, now let's get the sine of negative 45. So if I come up here and get the sine, it's going to be good, negative 1 over square root of 2. And what would the sine of negative 30 be? Negative 1 over 2. Does that make sense? We're doing this because it says exact. So we're not getting decimal approximations. We're keeping the radicals and fractions and everything the way that they are. Now, can I multiply these together? Please say yes.
Okay, yes.
Yes, okay, good. So if I multiply these together, this becomes square root of 3 over, what's my denominator? How do you write? Go ahead. Excellent. Usually we would put the whole number in front of the radical. So it's 2 times the square root of 2. And then what happens here with my SIGN? Because I've got a minus and it times a negative times a negative. Is that going to be positive or negative? Well, there's a couple of different ways you can think of it. I've got 3 negatives that I'm multiplying together, which 3 negatives multiplied together is a negative. Or I could keep the subtraction and then say a negative times a negative is a positive. Either way, you better have a minus sign here, okay? And then when I multiply these together, I get what? Good. And did we get a common denominator? Which is nice. That means now we can write the numerator as square root of 3 minus 1 over 2 square root of 2. Now, is that simplified? No, because what's in the denominator we don't want? All right, so what do I need to multiply by to get rid of the square root of 2 in the denominator? So I'm going to multiply top and bottom by the square root of 2. Be careful on the top, because we will need to distribute, won't we? So what is square root of 3 times square root of 2? Square root of 6. And then 1 times square root of 2 is square root of 2. So I've got square root of 6 minus square root of 2 over, what's my denominator? Oh, be careful. The square root of 2 times square root of 2 is 2, but it got to multiply by the 2 that was already there. Square root of 6 minus square root of 2 over 4 is going to be that cleaned up answer.
And it's so much stuff, it's hard for me to keep up, understanding, but once I look back, it makes sense.
Well,
we're just rewriting.
Yeah, I mean, honestly, on this, I doubt the trig is that hard. If you recognize, here's the trig part. The trig part is recognizing I can write this as a sum or difference using special right angles, okay? And if you can get that part done, and then you can find the formula and replace it, after that, this thing becomes an algebra problem. And so it's the algebra that's probably the hardest part of this, keeping up with the radicals and simplifying everything correctly. Is that sort of how you guys feel about it? Is it the trig or the algebra you're more worried about? We're not sure yet.
I just need to understand that all 3 triangles that would be drawn are all equal. Am I right in saying that?
What do you mean they're all equal?
Like all the sides that have a ratio to them, like the 45.
Yeah, if you draw a 45, 45, 90, you could get any of the 6 trig ratios from it, and it just depends on which quadrant you're in, what SIGN you need to use. But yeah, if you've got that part down, then that's all you have to get these replacements. And then after you get these values in, it's just algebra. Okay, now the cosine of 17 pi over 12. What's problem number 1 you might feel like you have on this?
Could you change it to degrees?
Okay, Elizabeth has a question. Would this be easier if we change it to degrees? For most of us, I think the answer is probably yes. So why don't we do that? What would we have to multiply 17 pi over 12 by to get it into degrees? What's our conversion? Good, 180 over pi. So now the pi's cancel. How many times will 12 go into 180? 12 goes into 18 one time. With 6 left over, 12 goes into 65 times. So 12 goes into 180 15 times. So now we've got to multiply 17 times 15, 255 degrees. All right, so we're going to rewrite this as the cosine of 255 degrees. Now, I know that's going to be in which quadrant? That's going to be in the 3rd quadrant because it's got to be between 180 and 270 in the 3rd quadrant. And if I were to put 255 degrees here, that means I've got 180 to get here, and this would be 75. This looks very similar to what we just did because we're looking for, and do you mind Megan closing the door? We're looking for an angle that would be 75 degrees in the 3rd quadrant. So I've got to figure out what would I want to add or subtract to get that 255 degrees. I can't do 180 plus 75. That's not going to work. So what might be something else we could use? Can we use what?
Okay, so the angle there is 75.
Yes, it is.
So could you kind of use what you used for the first problem?
So basically, Elizabeth thinks we could use what we used in the first problem. for the most part, I think that's right. The only thing we got to watch out for here is we're actually in the third quadrant. Now, if I were to ask you, since we're working here in the third quadrant, do you want to keep up with, like instead of 30 degrees, we'd call it 210 if we're in the third quadrant. And if we use, because 180 plus 30 is 210, and then we'd have to add what to it to get to 255? Are y'all okay with doing it that way so we keep up with what adds to be 255? Okay, so here's what I'm suggesting. We could take the cosine of 210 plus 45 as our replacement. And I know that because if I look here, my 180 plus 30 more, because that means I've got a 30-degree reference angle, right, is where the 210 comes from. And then if I add another 45 degrees to it, then I'll be at 255. Okay, so let's see if we can apply our sum to this. How would you want to do it? It'd have to be the cosine of what? 210 times the cosine of 45. At least this way we're working with all positive values. And then my SIGN is minus sine of 210 times the sine of 45. Very good. And I can use the same triangles. Now, since I'm in the third quadrant, you can decide, do I need to actually draw it in the third quadrant for the 210 to make sure I get the SI? The 45 is going to be a first quadrant, right? So if I were to do 210, okay, that means I've got 30 degrees here. So what would be the length of this side? -1. And that would mean that this side length is negative what?
Oh wait, it's a 30.
It's a 30. Negative square root of 3. Hypotenuse will be 2. Okay, good. So that's what I'm going to need for the 210. On a cosine of 45, since that's first quadrant, remember 45 is a 1 square root of 2, right? All right, so let's plug in values. Cosine of 210. So I'm looking at this one. Cosine is going to be what value?
Negative square root of 3.
Negative square root of 3 over 2. And then what would be the cosine of 45? If we rationalize it now, it would be square root of 2 over 2. Do y'all want to do that instead of writing negative, or instead of writing 1 over square root of 2? Well, when we're multiplying, we don't need a common denominator, but at least then we won't have to come back and rationalize later, okay? So we've gotten the cosine of 210 times the cosine of 45. We need a minus sign. Now, what would be the sine of 210? So if I go back and I look at this triangle, sine is what? Negative 1/2. And what's going to be the sine of 45? Yeah, it'll be just like this one. It'll be the square root of 2 over 2. Okay, so let's do a little cleanup. A negative times a positive is a negative, right? And square root of 3 times square root of 2 is? Oh, multiply. Square root of 6. Yeah, negative square root of 6 over denominator is, isn't it 4? 2 times 2 is 4. Okay, and then I have a minus times a negative times a positive. What's that going to turn into? A plus. Because a negative times a negative gives me a positive. And now if I multiply this, I get square root of 2 over 4. And my denominator is already the same. I can either write it as a single fraction where I keep the negative square root of 6 in front and add 2. Or if I wanted to put the positive one first, I could put the square root of 2 minus the square root of 6, whichever way you want to write it. over 4. Very similar to this because we're using those same ratio values. It's just by moving to different quadrants, it changes a few signs, okay? So that's one thing you'll notice is a lot of times, because you're gonna have to be able to rewrite these using those special right triangle values. It's gonna give you a lot of the same radicals in your answer.
Within that one, the square root of 6 is negative, then how is it the same as the one where the square root of 2 is negative? I don't get that.
Are you talking about from here to here?
No, like.
From here to here?
Yeah.
Okay, it's not the same. These are different answers because they were in different quadrants. What I'm saying is you're going to see a lot of the same radicals show up in the answers when you clean up. Okay, but you're right, the SIG ends are different, and so they do have different values. Okay, now look at this thing. This is kind of going the other direction because this looks like that sum or difference formula, and they want us to be able to write what it would be equivalent to if we were to put it back into this form. So look at that carefully. And first of all, since it's cosine times cosine first and sine times sine second, that does mean it's got to be the cosine of something. Now, is it going to be something that's added or something that's subtracted? Subtracted. So if I put 173 and I subtract 83, how much is 173 minus 83? Oh my. Can you find the cosine of 90 degrees? It's what? It's what? Cosine of 90. What do you think? A holla or holla? It's 0. Remember? Cosine of 0 is 1 because it starts high. Then at 90, it's back at the axis. So it's equal to 0. So depending on, like, I wouldn't know what the cosine of 173 is exactly, or 83. But if I use this sum or difference property, I can get it back to something that when I actually do that subtraction, I know what the cosine of 90 is. Okay? So you can go either direction depending on the values you have. Ready to go to the next page? So here are some cofunction identities. We've actually talked about these before. This is just a reminder. The cosine of 90 degrees minus angle theta. Okay, think about that for a minute. If we were talking about a right triangle, and this is angle theta, and I have the cosine of this angle, that's going to be equal to what? Since they're cofunctions, it's going to be the sine of something. Do you remember what it is?
It would be the sine of the one up there up top.
Exactly. Since this is angle theta, isn't this angle going to have to be 90 minus theta?
Yes.
Because these two have to add up to be 90. And so it's saying the cosine of this angle up here, which would be adjacent over hypotenuse, is the same thing as the sine of angle theta. We talked about these before. We're going to have some time to apply it here. What would that mean the sine of 90 minus theta is?
Cosine.
Yeah, cosine of theta. Okay. What about the tangent of 90 minus theta? Well, potentially we could rewrite it using sines and cosines, but we're trying to come up with cofunctions. So what is the cofunction of tangent? Cotangent. So that's going to be the same as the cotangent of angle theta. And we can go the other way too. The cotangent of 90 minus theta would have to be equal to tangent of theta. Secant of 90 minus theta would be equal to cosecant of theta. And the cosecant of 90 minus theta would be equal to the, yes. These are your cofunction. identities. All right, so what we want to do is to find a value of theta or x that satisfies each of the following. So we want to know what angle Q would be so that the secant of Q would be equal to the cosecant of 62. How would you find Q?
It's just 90 minus 62.
All right, do y'all agree? 90 minus 6. Absolutely, because these are cofunctions, secant and cosecant. Anytime, it's going to be the same thing, but with the co in front of it to be cofunctions. And that would mean that all I have to do is take 90 minus this angle to figure out what that has to be. And 90 minus 62 is 28 degrees. Ta-da. Okay, now, what would we do with this one? Same thing. So tell me how you would write, what would you write down to find angle Q?
Wouldn't be 90 minus negative 54 with adding.
Very good. We could do 90 minus negative 54, and that would give us 90 plus 54, which is 144 degrees. Notice it said find one value. We could have found other ways of expressing it, but 144 degrees is going to be one of the values that will be a cofunction. And on this one, now this is a little different. This p, remember, is actually pi. So it's 7 pi over 6. Now, do we want to leave it in radian form? Let's see if we can on this one, because instead of subtracting it from 90, what would we subtract it from? Okay, think for a minute. What is 90 equivalent to in radians? 180 is pi, so 90 would be pi over 2. Good. So angle x is going to be pi over 2 instead of 90 minus 7 pi over 6. Okay, now, if I want to subtract those, I have to have a what? Common denominator. What will it be? 6. So I'm going to multiply this first fraction by 3 over 3. That gives me 3 pi over 6 minus 7 pi over 6. That's what x is equal to. So if I clean that up, I get what?
Maybe 4 pi or
Yeah.
2, or do you
Yes, and reduce it down to,
2/3? 2.
and it'll be negative, won't it?
Yes.
Negative 2 pi over 3. Perfect. All right, so we have looked at our sum and difference of cosines. We have looked at our cofunction identities. Now let's look at sine and tangent sum and difference identities. Okay, these are also on your sheet. So there's for the sine, there's for the tangent. You'll notice tangent is the only one that involves a fraction. It's going to be a little messy. So if it's possible to avoid using tangent, you probably will try to do that. But let's write these down on here. The sine of angle A plus angle B. If I have some angle that I don't know what the exact value is, but I recognize I can either write it as a sum or difference that I do know exact values for, here's the formula. Here's what's different with sine. We don't keep sine and cosine paired up like we did in the cosine sum and difference identities. We got to take one of each here. So we'll start off with the sine of angle A, but we multiply it times the cosine of angle B. And here's the other difference. Our SIGN stays the same. It doesn't reverse like it did with cosine. So if I start with a plus, I'm going to have a plus here. And then I'll have to take the opposite. If I had sine of angle A here, I'm going to need the cosine of angle A here. And then this will need to be multiplied times the sine of angle B. So let me see if I can kind of summarize a little bit to help you sort of keep in mind what these formulas should look like. With the cosine, when we're talking sum and difference, it's always cosine times cosine sine times sine. So they stay paired up with the same thing, but the SIGN switches, right? On sine, what we have to do is switch the cosines and sines, but the SIGN stays the same. So one thing gets switched, but not both. All right. What do you think that's going to make the sine of angle A minus the B end up as?
Sine A times cosine B
Uh-huh.
minus
Uh-huh.
sine A times sine.
Perfect. That's it. All right.
That's all right.
All right, so we have now the sum and difference for sine. Let's look at the sum and difference for tangent. And remember, this is the one that I said is a fraction. So probably when you can avoid using it, you might want to, but there may be times you need to use it. So tangent of A plus B, your numerator will be tangent of angle A plus the tangent of angle B. Over your denominator will be 1 minus tangent A tangent B. So notice we keep the same SIGN in the numerator, we get an opposite SIGN in the denominator. So if it's tangent A minus B, our numerator is tangent A minus tangent B over, and what do you think the denominator becomes? Yeah, 1 plus tangent A tangent B. And these formulas are on your sheet. You don't have to have them memorized, but you'll find it's kind of helpful if you sort of know what you're looking for, especially because they put those plus minuses together on the sheet. So let's look and see if we can find the sine of angle negative 15 degrees. I don't know that one, but can I figure out some way to rewrite it so I can figure it out?
Negative sine negative 15 plus.
Well, I don't think I want to keep negative 15 because remember, I've got to work with either 30, 45, 60, or one of those quadrantal angles. Okay, I heard you say negative 45 plus 30. Okay, that would work. Could I also write it as 30 minus 45? That would be negative 15. So I'm going to write it as 30 degrees minus 45 degrees. By doing it that way, then all I need is a 30 degree and a 45 in the first quadrant, right? Okay, so if I were to do that, if this is 30, then this side is, oh, sorry, we put it this way. That'd be 1. And this side would be square root of 3, hypotenuse is 2. 45, what are those side lengths? 1, 1, square root of 2. All right. So let's see if we can take this and rewrite it using our replacement formula. That's going to be the same as the sine of 30 times what? If we're replacing this, it'll be the sine of 30 times cosine of 45, right? Okay, what SIGN do I need now?
Minus.
Yes, we switch these, but we keep the same SIGN. And then after the minus sign, we get cosine of 30 times the sine of 45, right? Okay. So looking at your triangle, sine of 30 is how much? 1/2. What's the cosine of 45?
Yes, square root of 2.
Good. In rationalized form, it's square root of 2 over 2. Minus cosine of 30? Square root of 3 over 2. And the sine of 45? Square root of 2 over 2. Good job. All right, so if we multiply this together, we get square root of 2 over 4 minus square root of 6 over 4, which is equal to square root of 2 minus square root of 6 over 4. We already had the common denominator. We can write it as a single fraction. Make sense? That's what I'm saying. You're going to see these same values popping up a lot because we're trying to get replacements that use either 30 or 45 or 60. And so it's going to give us the same ratios. Tangent of 13 pi over 12. All right. Now we can leave it in radians, or if you think I'm going to have enough trouble working with tangent identity, let's just get this thing in degrees. We can do that as well. What do you want to do?
I think we should do degrees.
Do y'all vote with Elizabeth and say let's change it to degrees? All right, so if we do that, 13 pi over 12 gets multiplied by 180 over pi. We did this a minute ago. I know 12 goes into 180 15 times. Pi's cancel. Now 13 times 15 is what?
190.
I'm sorry, say that again.
195.
195 degrees. Okay, so we want to figure out how we can rewrite the tangent of 195 degrees. All right, ideas. Gotta have to play with it just a little bit. I'll give you some hints. Think about if you're trying to add things, you're going to need something that's in quadrant 2 that would either have a reference angle of 30 or 45 or 60 in quadrant 2. So that would mean you'd need to know what 180 minus 30 is, 180 minus 45, 180 minus 60, and then see if you can add something to it to get 195. So if you did 180 minus 30, that'd be 150. And 150 plus 45, that would work, wouldn't it? Okay, so y'all good with that?
Can you write that down?
Yeah. What we did is we figured out, let me kind of draw you a little triangle so you can see the thought process.
Right.
Since 195 is here, and that's 15 degrees, the 180 plus 15 does not help me. So I know I've either got to find some angle that's in quadrant 2 that I can add something to get 195, or if I wanted to do subtraction, I could come up with something maybe in quadrant 3 that I subtract to get back. But I think for most of us, it's probably easier to think in terms of addition. So if I want an angle that's got a reference of 30 or 45 or 60 in quadrant 2, I would have to do 180 minus 30. That would give me 150, which is what we just settled on. And if that's 150, that means this one is 30, okay? And I can find all of the reference, I can find all the ratios for a 30-degree angle in the second quadrant pretty easily. And if I have 150 and I add 45 to it, that's how I'm going to get 195. So that's why I want to write this as the tangent of 150 plus 45. Does that make sense? Okay. Now, using my formula for tangent, let's look on our sheet here for a minute. And we wrote it as an addition, so that means I want to use all the SIGNs that are on top. So I need tangent of A plus tangent of B on top. So I'm going to have the tangent of 150 plus the tangent of 45 on top over my denominator is going to be 1 minus tangent A times tangent B. Is that making sense? 1 minus tangent A times tangent B. So here's what I'm going to have. I've got to get my ratios for a 30, 60, 90 that's in the second quadrant. And then I've already got my 45, 90 that's in the first quadrant because we used it over here, right? Okay, so 150, let me sketch that right here. That means I've got a 30-degree angle right here. And if I have 30 degrees here, what's this side length? 1. What's this side length? Negative square root of 3. And this would be a positive 2. All right, so this is the triangle that I will use when I need the tangent of 150. Okay, so the tangent of 150 is what? Well, look carefully. Tangent is what ratio? Opposite over adjacent. Won't that be, and if you want to rationalize 1 over negative square root of 3, what will that become? A negative square root of 3 over 3 is going to be the tangent of 150 plus, now the tangent of 45 is what? If this is my 45-degree angle, opposite over adjacent is, say it again? 1. Okay? And we'll clean that up in a minute. Over, now I need 1 minus, I'm still using the tangent of 150. It's going to be the same thing I found here, which is a negative square root of 3 over 3, times the tangent of 45, which is 1, right? Okay, so now we just need to do a little bit of cleanup. What do you think we should start with?
Could you distribute that negative and then make, or the minus sign or whatever, and so you would make that positive square root of 3 over 3, and so it would cancel out with the top. And then,
Okay, well, hang on a second. Let me make sure I'm following what you're saying. If I've got plus signs and minus signs, can I cancel out pieces?
yes.
No, I can only cancel out factors, so they have to be multiplied together. I can't cancel these because they're being added and subtracted. But should we maybe write it as a single fraction? Please say yes. Yes, okay. We do want to write it as a single fraction. We don't want to leave this as a 2 separate fractions in the numerator and 2 separate in the denominator. So wouldn't I need to multiply 1 by what to get a common denominator? 3 over 3. So here's what I have. I've got a negative square root of 3 over 3 plus 3 over 3, right? And I'm going to write that as a single fraction in just a minute. Now, in this denominator, what happens when I have 1 minus a negative square root of 3 over 3? Yeah, it turns into a positive, and this times 1 is just this. I've still got the same kind of issue where this has to get multiplied by 3 over 3, right? And that's going to turn the denominator into 3 over 3 plus the square root of 3 over 3. Are we okay so far? Now, here's what I would do. Come down here. First of all, can I combine this into the negative square root of 3 plus 3 over 3? And we said anytime we have a fraction divided by a fraction, that's the same thing as multiplying by the reciprocal. If this were combined, it's going to look like this. And if I take the reciprocal, what goes on top? 3. What goes on bottom? Yeah, 3 plus the square root of 3. And now what can I do with these 3's? Cancel. Okay. So we have the negative square root of 3 plus 3 on top over 3 plus the square root of 3 on bottom. All right, this still looks like a mess. And for good reason, because we're not supposed to leave a radical in the denominator, correct? But how in the world are we going to get rid of it when my denominator is 3 plus the square root of 3? This is an algebra thing. It's not a trig thing. multiply by, say it again.
Just a square root of 3?
No, if I multiply by the square root of 3, I'd distribute, and I'd get rid of this square root of 3, but then I'd create a new one. I've got to multiply by something called the conjugate. How do you get the conjugate of 3 plus the square root of 3? 3 minus the square root of 3. It's okay if I have radicals in the numerator. I just don't want them in the denominator. And if I'm going to multiply the denominator by 3 minus the square root of 3, I'm also going to multiply the numerator by 3 minus the square root of 3. I know this thing is messy because of the algebra, guys, okay? I won't give you a bunch of hardcore things like this on the test, but by going through them together on the notes, it's going to help you in homework. Hopefully you're going to feel like the test is easy after we've done these. Now, I got to use FOIL both places. When I multiply the numerator, tell me what I'm going to get. The negative square root of 3 times 3 is what? Well, negative times a positive is still a negative, and it's going to be a negative 3 square root of 3. That's multiplying first times first. What happens when I multiply outer times outer? A negative square root of 3 times a negative square root of 3 becomes positive, and what's my number? Square root of 3 times square root of 3 is? Which is? 3. So I get a plus 3. Because negative times negative is positive. Square root of 3, when it's squared, is just 3. Now let's do inner times inner. What is 3 times 3? I got another plus, and that one didn't have any radicals, so 3 times 3 is just 9. And then what is positive 3 times the negative square root of 3? Positive times negative is?
Negative 3.
Negative 3 square root of 3. Now I can clean this up in just a minute. But I want to see if you can tell me what's in the denominator. The reason we did this is so that outer and inner would cancel, and we'll end up with, we'll end up with no radicals in the denominator. So if I multiply this, first times first is 9. The outer and the inner are going to cancel, and then what's last times last? What do you think it is? Square root of 3 times the negative square root of 3 is negative 3. Positive times a negative is a negative. Square root of 3 times square root of 3 is just 3. How are we doing? Okay, let's put together like terms now. In the numerator, what is 9 plus 3?
Wait, what?
Let's add yeah, the denominator is 6. You're right. You were just working on the denominator. But the numerator, if I add 9 plus 3, I get 12. And now what do you get if you add a negative 3 square root of 3 plus another negative 3 square root of 3? Think of that radical as if it were an x. What would a negative 3x plus another negative 3x be? That would be a negative 6x. So what is, like I said, think of that radical as if it were an x. What is a negative 3 square root of 3 plus another negative 3 square root of 3 going to be? Minus 6 square root of 3. So we have at least combined this where now it's a single fraction, no radical in the denominator, but guess what? Can it reduce? Because we have a common factor, we can factor out a 6 in the numerator and reduce down. That would give me a 6 onto 2 minus square root of 3 over 6, and when those 6's cancel, my final answer is 2 minus square root of 3. All right, so do you see why I said when you can avoid using tangent, you might want to? It can get nasty because of those radicals and the fact that you've got fractions. But by multiplying through by the conjugate, a lot of times that will help things clean up just a little bit.
How do we plug in the check?
How do you plug in and check it?
Is there a way to do that?
That's an excellent question. Let me show you something you could do. Let's say we did all this and we're thinking, I don't know if this actually would be a logical answer.
Like if we had multiple choice and we could work backwards with the answers.
No. You're not doing that. But let me show you what you could do. Let's say we got 2 minus square root of 3 here. So we're going to type 2 minus square root of 3 into this calculator.
Okay.
And we're going to get this ugly little decimal. Okay? I want to see if I'm in, now let me check my mode. I want to put it in degrees because we changed it to degrees. And I want to find out what the tangent of 195 is. Let's see if it's the same ugly little decimal. Ta-da!
I like that.
So that's how you can, I'm glad you asked that. So you could do that on all of these that we have done and double check to see, is my exact value coming out to be the same as what the approximate value would be doing it in the calculator.
I can get this, it's just gonna take me a while to work through the problem. Might need some additional time to